This video review is devoted to primarily natural log of x with a little bit of a snippet of e to the x. And the reason I'm devoting a video to these two functions, and especially natural log of x, is it's a super popular function throughout all of your calculus career, and sometimes people don't feel very comfortable with natural log of x. You should become comfortable with it because it's going to save you a lot of time and effort and get you a lot more points. So here's a graph of natural log of x, and I'm just going to point out a couple characteristics that you have to implant in your brain. It has an x-intercept, 1, 0. It has a vertical asymptote, which means it's always going to stay in positive x territory. There is no horizontal asymptote, meaning when it's heading this way, it's not going to hit an asymptote or it's not going to approach an asymptote. It's going to continue to increase forever and ever. And you should realize that natural log of x is really just a special form of a logarithmic equation. It's the log base e. And log base e is so famous and so common, it gets its own name, natural log of x. And as I alluded to, the natural log of x is only going to accept positive inputs or positive x values. Of course, that would change if you shifted it. So for example, here we shift it 5 units to the left. So now the domain goes from -5 to infinity. Think about it this way. If you plug a -3 into here, that ends up being natural log of 2, which is okay. But if you plug a -3 into here, that doesn't work because that graph is not within, or that's not within the domain. All right, let me remind you of some properties of logs. And these are properties of all logs, but since natural log is a very famous log, it's a property of natural logs as well. If I have an exponent, this is a 4 squared, that exponent can come out in front as a coefficient. Weird, huh? If I have something inside the natural log that is multiplied, a times b, I can turn it into 2 logs connected by addition. And if I have if I have a quotient or division going on within the log, I can turn that into subtraction. So your natural question should be, why would I ever bother learning these 3 properties? Here's why. The AP likes to check your knowledge of properties in a tricky, somewhat underhanded way. So let's say you're working through a problem. I don't have a problem here, but ... just means you're doing a bunch of work. And you do a bang-up job, and you end up with natural log of 7a to the 3rd power. You're really happy with yourself until you look at the multiple choice answers and you realize that's not one of the answers. So you think that you've screwed up when in fact you haven't. What the AP has done is they've taken this answer and they've used log properties to rearrange it to see if you can connect what your answer is with a different form. So what they really did here is they said, hey, let's put that exponent of 3 out in front. And then that's using the power property. Then they said 7 times a is really like this. And if I distribute the 3 to both of those terms, voila, I have the answer. So that's why you would learn those properties, partly. You really want to learn those properties because it's just good old math, but on the AP test, that's why you want to know those properties sometimes. And this is your natural log. Let's do a super abbreviated version of e to the x. You're much more comfortable with e to the x, I'll bet, but know that it has a y-intercept of 0, 1. You've got yourself a horizontal asymptote over here, and there is no vertical asymptote. This continues to climb forever, but there's no border or asymptote over here. That's probably all I need to say about e to the x. And the last thing I'm going to do is I'm going to give you some intuitive thinking problems using natural log of x and e to the x. And it's kind of preparation for the type of thinking that you will absolutely positively need later on in this course. So for example, what if I said, hey, let's approximate. We're not worried about an exact answer. 7 divided by natural log of 1.001 or 0001. Okay, so your mind would daydream about the graph of natural log, and the natural log of 1.0001 would be like right here. That y value is super tiny. So I would say 7 divided by super tiny, and that's a positive value too, by the way. So for our sake right now, we're just going to call this positive huge. We could get a real answer for that, but I'm not concerned about that. When I say positive huge, I just mean like 32,000, something like that. That's all we care about right now. All right. So similar situation, 7 divided by the natural log of 0.9999. 0.9999 is about right there. So this is really equivalent to 7 over a negative number that is super, super tiny, which using the same logic is like a negative huge number, which seems like an oxymoron, but what I mean by that is, let's say, negative 8,000. That type of thinking seems a little weird. It seems like we should have exact answers, but you'll see why later in the course, why it's good to be able to think like that. All right, if I do 12 divided by natural log of 0.0001, natural log of 0.0001 would be way down here, way down here. So that's really a 12 divided by a negative number, and it's a huge negative number. You know, I might be down, by the time I get to an x value of 0.0001, my y value might be at negative 8,000, I don't know. So this is very close to 0. So I'm going to say close to 0, but we know it's not exactly 0. This is why we're using those squiggly equal signs so that we never have to be exact. Final intuitive example. Negative 8 divided by e to the negative 3,000, negative 300. So this is equivalent to negative 8 divided by, now what is e to the negative 300? I don't know an exact answer, but I know by looking at the e to the x graph, negative 300 is way out here, which makes my y value super tiny but positive. So I would call this a positive tiny value, which makes this become a negative huge number. Kind of like we're approaching negative infinity. Think of it like a negative 8 divided by a positive 0.00004. That gives me a huge number, and it's negative. So if it's disturbing you right now that we're not coming up with exact answers, I'm going to call that 0-ish. That's okay. You'll understand why we would do something like this later. I'm just showing you the type of thinking that you might need to do with a natural log or an e to the x style function. All right, we'll catch you later.